Hello everyone, so we're going to continue with our 4.3 and now talking about greatest common divisors and what's also at the same time about least common multiples. We'll see how they connect. First of all, what is that? The GCD. So the GCD of two numbers, A and B, we call that its greatest, so this is greatest common divisor. And so the word it says itself is the biggest divisor that they both have in common. Biggest divisor, remember that means factor. But it actually has a little bit better. What it means is that it means, in particular, that means that D divides A and D divides B, and any other divisor of A and B must also divide D. That's another thing that it means, but let me not write that up. I'm sure that most of you know what that means, the greatest common divisor. We have looked at these things before, I'm sure, in other courses. How do you calculate this? Let me quickly show you how to calculate. So we will do several techniques. So the first technique is prime. So the GCD, calculating GCD. Let me calculate. So calculating GCDs. So method one is using prime factorization. We know now that every number can be factored. So let me give you an example. I want to calculate the GCD, let's say, of 98. So GCD of 98 and let's say, let me think a little bit, 28, 60, 84. Okay. So what you can do, of course, is start looking for divisors and then find the biggest one. But that's sometimes a little bit guessing, and as the numbers get bigger, it's harder to see. Of course, we see the GCD of 6 and 8. Okay, it's both divisible by 2, but nothing else, so that's rather easy to see. But this is already a bit harder to see. So how does it work? Well, we're going to do the prime factorization of both of these numbers. So remember how I did this. I start with the smallest prime, doesn't go in there, yeah, because 8 is, it's an even number because it ends in 8. So if I divide by 2, I get 49. So does 2 go in there? No. So does 3 go in there? Remember, that means that the sum of the digits has to be divisible by 3, but that's not the case, that the sum of the digits is 13, which itself, the sum of the digits is again 4. So no. So what about 5? It should end in 5 and 0. So 7. 7. Yes. So then there's no criterion for 7, by the way, if you're wondering. So for 7, you can only check it by using your calculator. 7, of course, 7 goes in 7. So 1, and once I have a 1 here, I know I'm done. So what I found is that 98 is 2 times 7 squared. I'm gonna write everything. Group all the same primes together and write them as with a single power. It's going to help me to find the GCD. Now I have to do the same for 84. So 2. That's the first prime number. Yes, I can divide by 2. I get 42. Divide by 2 again. I get 21. Can I divide by 2? No. What about 3? The sum of the digits is 3. So yes, it's divisible. So that gets me 7. Can 3 in there? No. But 5 in there? No. But 7 goes in there. I know this is stupid because you see it, of course, but I just want to show you that's how we do it systematically. So what does this mean? This means that 84 is 2 squared times 3 times 7. Okay. So what is now the GCD? How do we find the GCD? So the GCD of these two numbers, so we have, this is the prime factorization. How do you find the GCD of these two now, 98 and 84? We take for every prime the smallest exponent in both in both cases. So what does that mean? What is it 2? In this one it's 2 to the power 1, and this is 2 to the power 2. So the smallest one is 2. So this will be just 2. The next prime is 3. So we have 2 to the power 1. What is the power 3? I'm not going. Normally we don't do this, but I'll show you. 3 has the power 1 here. What is the power of 3 here? 0. So this will have, the smallest will be 3 to the 0. In other words, 3 will not be part of it. So I'm going to write it down for now, but from now on, once we're used to this, we're going to just ignore this, right? Same for 5, right? 5 doesn't occur in either one. What about 7? 7 occurs to the power 2 in the first and power 1 in the second. What's the smallest is 7. So 7 to the power 1. So, of course, these are just 1. This gives me 14. Okay? And so the general technique is, so you write A as these powers, M1, P2, M2, Pk, Mk. So this is the prime factorization of A. So the Pi's are primes. Which primes? Well, 2, 3, 5, 7, and so on. But let's say that, let's just give them sometimes 2 and 3, and so you see some don't appear. So I just write them. Let's only consider those that actually really appear, right? As of B, we do the same. P1 is, and now let's call this K1, because the exponents are going to normally be different exponents, right? Okay, I used K here, so let's call this S. And so here, the same S. Oh, S, okay, S, sorry. I don't like these general things, so I hope you see what, I'll do it on another example. And so what is the GCD now? You take P1 and then take the minimum of these two powers, M1 and K1. And that's going to be the power of P1, and so on. And you do it for all the primes that you have. So MS and KS. Okay. This is very, very hard to parse if you're not mathematically inclined. So let me give you another example here. So suppose A is the number 2 cube, 5 square, 7 to the power 3, 13, and 23 to the power 2. And B is the number 2 cube, 5, 7 square, 13 square, 17, 23. And let's put 20, yeah, 20, let's put it that way. So this is the prime factorization of these two numbers. Okay, you can work it out what the numbers are, but who cares now, right? Okay, so what is the GCD now? Well, as I said, for every prime that occurs, we have seen if a prime doesn't occur like 5, it's pointless to look at it. In fact, it has to occur in both, okay? So 2 occurs in both, and what's the smallest power? Well, it's 3 in both, so that's the smallest then. 5, the 3 doesn't occur, so I'm not gonna talk about it. 5 occurs in the highest power. The highest power is 2, the smallest is 1, so it will be 1 here. Let me put it, for emphasis, put a 1 there. What for 7? 7 will be the highest power, the smallest power, sorry, is 2, right? So it's always so remember, let me write it. Take smallest power of each prime. That's our strategy. Okay, 11 doesn't even occur, but 13, that's the highest power is 1. 17 occurs only in once, so the highest power is, sorry, I misspoke. I keep saying highest for some reason, I don't know why. 13, the lowest power is 13, okay, down from 1. 17, the lowest power is 17 to the power 0, so it doesn't, we're not going to write that. 19 doesn't even occur, and 23 is the next prime. I don't have my list anymore, so that would be 23. So this is the GCD, just from the prime factorization we can read that off. Now there is something very, as I said, there's kind of a cousin of the GCD is the LCM, that is the lowest common multiple. You know this perhaps better as the least common denominator, least LCD. But of course, denominator terms, that is when we're dealing with denominators. But what you calculate is the least common multiple. And so what is that? that is just, as the word said, is the smallest number that is a multiple of both of them. Okay, so for instance, the lowest common multiple of 4 and 6, it's not 24, it's a multiple. 24 is a multiple of 4, multiple of 6, but it's not the smallest one, it's 12. Okay, that's for all of you that have looked for the LCD, know that this is how it works. Now, how do you calculate this? The technique is exactly the same when you have prime factorization. Okay, using prime factorization. How do you do this? Well, exactly the same here. So let me write it here. Let me get rid of this LCD part. Take in the prime factorization the highest power of each prime. Okay, so let's do this on our first example here that we had. So we have the, let me write this a little bit. Okay, I can erase this, right? We have this here, we have the prime factorization on the right. Okay, so what's the LC, the least common multiple, the LCM, least common multiple of 98 and 84? Well, now we do the same. Every prime, we look at the highest power. 2 occurs to the power 2. What about 3? It doesn't occur in one, so I don't have to look at it. No, it does occur in one of them, so I have to look at it. And the highest power, therefore, is just 3. What's the highest power of 5? That, if it doesn't occur in either one, then I can ignore it. What about 7? That's 7 squared. Okay, so this is this number, which is, by the way, if you want to know what that number is, it's 49 times 12, that is 588. Okay, now I'm going to show you a nice identity. 98 times 84, these are the two numbers we talked about, right? What is that? 98 times 84 is 8,232. Let's now take the LCM and the GCD of these two numbers. The LCM was 588 and the GCD was 14. Let's multiply those. 588 times 14. Lo and behold, it's the same number. And if you, I'll let you think a little about it. I'm not going to prove it, but it's kind of explained by this one. Here we take when we take the GCD, we take the smallest power, and here we take the biggest power. But if we put them together, then we have taken there are only two types, right? There are two numbers. So there's there's a power that is the least and there's a power that is the biggest. If it's the least, I put it in this bunch. If it's the highest, I put it in that bunch. But if I put them both together, I've taken all the power. So I've taken all these guys and I've taken all these guys. What does that mean? If I have a product of all these guys paired with all these guys, that's just a product of A and B. So the identity that we have is, and that is going to be important for the next method, that the LCD of A and B times the GCD, the LCM, sorry, I should use the right terminology here. So the least common multiple of A and B times the greatest common divisor of A and B, if you multiply these two, that's the same as just multiplying your two numbers. Okay, so I didn't do it here yet. What is the LCM of A and B? Of the example that I have here. So let me just now erase here. I'm not going to check this other thing because there are big numbers. So what is the LCM of A and B? So now for every prime, I look at the highest power. That would be 3 here. 3 doesn't occur in either one, so don't mess with it. 5, the highest power is 2. The highest power of 7 is 3. 11 doesn't occur. The highest power of 13 is 2. What about 17? Well, 17 occurs once, so the highest power is 1. 23 squared. No, so that's the LCM, and the other one was the GCD, which unfortunately I erased. So I'm sorry, I should not have done that. Let me write it very quickly. The lowest power, the lowest power, the lowest power, the lowest power, and the lowest power, right? That was the thing. And let me show you again. Every of these factors that we have here occurs either here or here, right? Right? You can these two, this is this guy. Oh, I copied this wrong. This was the lowest power 7 squared, right? So Okay. This one is here, this one is this, this one is that, this one is this one is that. So you see they're not always in the same place. This one is in this one is in here, and this one is in there. But every single one is exactly in one of those. So if I multiply these two together, is the same as multiplying these two together. Again, what I said here. Okay. That's one technique, but it's not the best technique, because prime factorization, if you remember from the previous video, is a difficult problem and it's time consuming. Even for small numbers, it takes a little while to do this, right? So there is a much faster method, and that's the method of which is the book calls the Euclidean algorithm. I don't know. That's the names that they give. When I use the word Euclidean algorithm, I use it slightly differently. It kind of does the same, but okay, fine. What do we do? So let's do, we have our two numbers, we know the result, 98 and 84. So let's work with that. We know it's going to be 14. So the GCD of 98 and 84. So the Euclidean algorithm refers to the division algorithm. This uses the division algorithm. Remember that I said it's a reported algorithm, so I want you to use this. That's why I also say you have to use it in the quiz. You will see. How do you do this? Okay, we have the two numbers, and you take, of course, the biggest number, 98, and you do the Euclidean division by 84. So how many times does 84 goes in there? One time, and what's the remainder? 14. Okay, but now here is where things start becoming differently. Sorry, let me just. It is different. We don't confuse this with the calculations that we were doing when we're doing modular exponentiation. What we're now going to do is, so let me highlight. So we have this pair. Sorry, highlighting with this. I'll do it yellow. Okay. We start with this pair, and so we divide the biggest by the smallest. Now we consider a new pair, and the new pair consists of yes, this one and, sorry, no, I got myself a little bit confused. Yes, this one and this one. So the number that I was dealing with, one of the numbers I'm dealing with, but now also, so be careful. This is the diff. I'm not taking the diff. I'm taking the element that I divide by and the remainder, and I repeat the same calculation. In other words, I do the division algorithm with 84 and 14. So how many times does, let's calculate this. How do you do this? 84 divided by 14, that is 6. Oh, it goes there exactly 6 times. Okay, so we get here plus 0. Okay, so let me mark. So it's now these two numbers I take. In the next step, what are the two next numbers that I take? It's kind of silly to do it, but I'm just going to do a better example later. I would take this number and this number, right? The previous number that I've been working with, the smallest of the two numbers I've been working with, together with the new number, that's the remainder. So if I do that, how many times there's 14 in 0? Well, that is, of course, 0 plus, once we have 0 here, then there's nothing to do anymore, right? So 14 is the remainder here. So what the number that we get here on the end, when you have a 0 here, it's this number. So if you want, it's 0 plus 14. I don't know how to say this, but it is, when you have a 0 here, this is going to be your GCD. So 14. Let me do it on something where we have where a little bit more works than it's bit. So let's calculate the GCD of 91 and 287. Okay. What do you do? Well, we start with these two numbers, right? And we do the long division on Euclidean division on that. So of course we take the biggest one. 287 is how many times 91 plus a remainder. Okay, so here I need to calculate the diff, which is very easy. You just do 287 divided by 91. That is 3.1, so we know it's 3 times. And what is the remainder? So 91 times 3 is 273. So this number is 273. So what I'm missing is a 14. Okay? So what is this? This is the long division, division algorithm on these two, what I call yellow numbers. Okay? These are the two yellow numbers that I use. What do I do the next step? The next step, I use my smallest of my number that I've been using together with my remainder. And I use these two now to do the division algorithm. So we do 91 here and 14 there. How many times does 14 go in 91? So 91 divided by 14, that is 6.5, so 6 times. That is, this number would be 84, right? So we need another 7. You following that? Okay. So let me erase this 84. Oh, this was it. What do we do now? The next step, I'm going to use the smallest of the numbers from the previous case, and the new number will be the remainder. So I do now the same thing with 14 here and 7 there. Okay? This goes there 7 times plus 0. And once I have 0, I know it's the last one that I found that is going to be the GCD. So if I get 0 here, then this is the GCD. And so in other words, I keep doing until I find 0. So the GCD is 7. Let's do a couple of other ones, because it's, let's do the GCD of 414 and 662. Okay, we could do prime factorization, the first method, but I want to do this using the Euclidean algorithm, and I want you to learn this one. So I don't know what I'm going to still think about, but I'm going to do a test about that, but I might very well do a test on that, because it's a very important technique. We're going to have to use it all the time. Okay, so yes, I will do a test on the quiz on this, but there's one more thing is going to come, so be patient. It's not done yet what we're going to do with this, but okay, let's do this. Okay, so we have these two numbers again. Let's do with the colors a little bit, that you can, I hope it helps you see what I'm doing. So these are the two numbers. Of course, I take the biggest one to start, and 414. Okay, that goes there only once, right? And then what's the remainder? Well, it's the difference, and that seems to be 8, 22, 4, 2, 248. Okay, yeah. So that's the first step. Now these two numbers, let's make them green, will be the new numbers that I'm going to use to do the division algorithm. So 414, of course, is the biggest. Why? Because the other one must be, the remainder is smaller than the divider, right? So 248. Okay. Remember, notice I'm not using the quotient. I hope the one I'm not using there, right? How many times does that go in there? I think also once only. And what's the remainder then? That would be 166, right? Yeah, 166. Okay, repeat. Now we're going to use the smallest of the previous numbers, and the new number will be the remainder. These are the two that I'm going to put here. So 248 and 166. Oh, many times does that go in there? It's kind of annoying. It's only once. Okay, that's why it seems to be taking a little while. So what's the difference then? 82, right? Yeah, 82. Okay, so next color, we're going to take this and this. Okay, so we have 166, and here we have 82. How many times does that go in there? 2 times, I think. This is going to be 164, so what is missing is another 2. Okay, so great. Let's get rid of this. And why do we keep going? We keep going because this is not 0 yet. Okay, so once it's not 0, I'm going to pick it for my next one. Let's make it in pink. This one together with this one. 82 is, and sorry, I should have done the pink ones first. And So I'm going to do here and here. So I take 82 and 2 here. How many times does 82? Well, it goes there quite a lot. 41 times. And then the remainder is 0. Ah, I got a 0, so this is my GCD. Okay? So the GCD is 2. I'm going to come back to this, but before I do this, I want to now calculate what's the least common multiple. Can I use this method to use the least common multiple of the same two numbers, 414 and 662? Well, there is no method using division, but what do I know? I know that if I multiply this number, so I want to know what is this one, right? But I have this formula here. Look at this formula. Okay. This formula says that if you want to calculate the LCM, take the product of the two numbers and divide by the GCD. Okay, so this number is going to be 414 times 662 divided by the greatest common divisor of 414 and 662, which I just calculated to be 2. So it's 414 times 662 divided by 2. Now it's a big number, but that's what it is. It's 414 times 662 divided by 2 turns out to be 137,034. That's what it is. And you can see that this could be a lot of calculation if you have to do this with prime factorization, right? You see how big the numbers become. Okay. Now, I want to do perhaps... Yeah, let me do another one before I start with this. Continue with that. Where I want to do, let's see, what's the number here? Sorry, I need to get a nice combination of things. Let me see here. Okay, I'm gonna just let's do one more thing. What do I want to do? I'm sorry, I'm looking for an example and I don't know where I wrote it. I don't find it anymore. So I'm going to take a random thing here. Okay, give me a sec here. The GCD of 24 and what was this? No, that we had. No, that number. No, okay, sorry. Give me one time. I want to write down a number. I wanted to calculate the GCD of. Okay, here. I want to do the GCD of 84 and 65. Okay, using this method. Okay, here we go. 84, we go in there one time, and what's the remainder? 19, right? Yeah, 19. Okay, so again, if you want my color scheme, we started with yellow, right? So these are the two numbers. Now the next two numbers I'm going to take is the smallest of the previous one and my remainder, and use those two. So that is 65 and 19. How many times does 65 goes in 19? 65 divided by 19. I can do this, it's 3 times, right? But okay, 3 times, okay, and that is 57. So what we're missing is an 8. Okay, so let me get rid of this intermediate calculation. Keep doing this. Okay, so the next one would be these two numbers that I'm going to do long division. So 19 and 8. Be careful that don't say, oh, it's 2 times 9 is 18, right? But not 2 times 8 is 19, right? Don't get confused there. Okay, so that's 2 times 8, that's 16 plus 3. Okay, so what are going to be the next two numbers that I'm going to work with? 8 and 3. Okay, so let me do this here, 8 and 3. So we have 8 equals 3, so 2 times 3 plus 2, right? Okay, so the next two numbers I'm going to work with are going to be these two, 3 and 2. Okay, so here's 3, here's 2. 3 goes there in one time plus 1. Okay, good. What's the next number I'm going to do? Yeah, well, it seems a bit weird, but I'm going to use this. I'm going to use this number and this number. So 2 and 1. 2 and 1. Well, 2. How many times is 1 and 2? Well, 2 times, right? For 1, that's a silly thing, because the remainder will always be 0. The remainder has to be smaller than the guy that you divide by. If you divide by 1, there's only one number smaller, that's 0. So we reach 0, so this is the GCD, 1. Is that possible? Of course that's possible. And it's actually an important situation. So we have calculated now that the GCD is 1. And we say that 84 and 65 are relatively prime. What does it mean? Let's think about it, what it means, what's the prime doing there? Well, let's think about the prime factorization of these two numbers. What it tells me is they cannot have anything in common. Because if they have anything in common, that by my principle of taking the smallest power, I would take at least that one would occur in it. Right? That would be one of the factors. For every prime that occurs, if there is a prime that occurs in both numbers, it will show up in the GCD. But if the GCD is 1, that cannot be. So relatively prime means that the primes are different. That the primes that occur in 84 in the prime decomposition of 84 are completely different from the primes that occur in 65. That is what relatively prime means. Okay? And that's an important concept. And in fact, you can also say when several numbers are relatively prime, means that they pairwise relatively prime and so on, but let's keep that for later when we need it. But this is a notion that we're going to read before, and you can calculate this. It means that the GCD is 1. It will happen if, at this point you would have seen it already, if you get the remainder. No, sorry, that's not true. Yes, right. Because if the remainder is 1, next time we're going to divide by it, and the remainder is going to be 0. So that's okay. Okay, so, but, and now comes to an important fact that I'm going to use. I'm going to show it here first. I'm going to do a little bit of manipulations, and please bear with me. It's in the beginning you say, what on earth are you doing? Right. Okay, let's look at this here. Okay, so I'm starting now, right, so this was the direction in which we worked before, right, from the top to the bottom, but I'm going to go the other way around now. I'm going to start with this equation, okay, and what does this equation tell me? Sorry, okay. I apologize. I'm going to start with this equation. This equation was telling me it stops, right? If I remainder 0, then I'm done. So this is the equation I'm going to start with, okay? And I'm going to solve for the remainder in this case, so which means that 2 is equal to 166 minus 2 times 82. So I bring the 82 to the other side. But now don't forget they were colored. Let's keep the coloring scheme that we had. This was 2 and this was 82, right? Okay. Now 82 was also the pair 82 together. Now how the things work, right? I'm going backwards. So we also had the pair 166 and 82, right? So 166 and 82. Notice that I have 82 here now, and I can solve for 82. So I'm now replacing this 82 by the two numbers that I have here. That is, and I'm going to keep the coloring. This is a bit weird, this coloring, so I'm sorry about that, but that's how I can best show you. 166 minus 2 times, now 82, this 82 I'm going to replace by this, to bring this to the other side. So I get 248 minus 1 times 166. Now remember, these were actually, right, so this was the blue number, And the 248 is actually was a red number, right? That was the number that I used in the case that comes from the time before, okay? So what we have here is 166, a blue 166 here, another blue 166 here. Why? Let's combine them as one single 166. So, okay, I'm gonna keep my color. I'm sorry, this is a lot of coloring, but it is important. So here's my 166. So what is the coefficient of this 166? I have a 1 here, and what do you have there? A -1? No. You have a -2 times -1. Don't forget there's a -2 in front of here. So you have a -2 times -1, a +2. So +2 here. And then -2 times the red guy. So here's the red guy. Okay? And that was 248. Sorry, I don't know why I put it so far behind there, but that's what I mean, right? This times that. So let me write it a little bit shorter here. We have 3 times 166 minus 2 times 248. And where this was the red number and this was a blue number. But this 166 in the previous step was also a red number. So now this is also a red number, right? Oh, that's not red. This is red, right? Now I'm looking. Remember, I'm going up the line here, right? Although I'm writing it down, I should have actually also put this over there. So let me write down what I have at this level here. So remember, this is still this little 2 here, right? So I should have gone up here. So I'm going to copy this line and just put it here. So this is 3 times. Let me actually do this. It's easier, but just actually copy it. So then so I'm going to put it here, right? Okay. Now so let's say let's keep a little bit track of what I've done. I have used this equation that was this line, right? Then I replaced this 82 using this line. So I have now used that one as well. The next line that I have not used, the one on top of it, is 166, and this tells me that I can write 166 because it's always on its own here. It's the remainder is always on its own. I can write it in combination of these two guys. Okay, let's do that. So that is 166 is 3. So I'm going to replace 166 by 414 minus 1 times 248. Let me keep writing the 1. It's kind of silly, but just so that you see where everything comes. So these are now, let's see, this is a red number, and this was already called a green number. Okay. Notice that I have now. Wait. This is just this one. What about that? Well, it's there. That one I'm not going to replace. You say, oh, Professor, but it's here. Wait, step by step. Okay. This is very important. You cannot skip a single step here. You have to do it really detailed step by step. So -2 times, oh, sorry. So I just copy this now. I'm not doing anything with that yet. So this is red, right? Sorry, red. I have now 2 reds here, so I should combine them, right? These 248s, I should combine them, okay? Can you see what I'm going to write it here. What's the coefficient of 414? That is 3, right? So 3 times 413, plus how many times are going to have, well, plus, perhaps I should not write a plus yet. What's the coefficient of 248? Is a -2 here, and here it's a -1 times 3. So -3 minus 2, altogether -5. But let's keep the coloring. So this was red, and the other guy was green, right? Okay. Now I go to the next line. So I've done with this line. What's the next line? The next line gives me 248. Here's my 248, but it's now green, has become green. In that previous line, it was a green number. So I have now this, and I can use this line to rewrite 248. What about 414? Well, I just don't do anything with that. 3 times, so this is 3 times, 414. So I'm not copying that, -5 times, but here I'm going to write 248 as 1 times 414. Oh, sorry, no, it's the other way around, right? I'm putting the wrong order. It's 662 minus 1 times 414. Okay, but let's use the coloring scheme. This is a yellow number. This is a yellow number, and the other one is a green number. Okay, notice that I have again two 40/14s. There I should combine them again, right? Each time. So each time there's two steps, right? You use this. You use one of the equation that you have not used. The next equation above that you have not used. You use this to rewrite the remainder in terms of the other two. That's the first step, and then that's what we do here, right? We replace this 248 by this combination, but then we combine whatever we have. These two green 44/14s we have to combine. So what is that then? If I combine this, that is we have a 3 there and a -5 times -1, 5 there. So 8 times 414 minus 5 times 662. Right, so let's see, this is the 414, and this was a yellow guy, right? Now I reached actually, in the next, there's no next step anymore. In next step, the only thing was, we started, this was yellow, so if you want, this actually was also yellow. But look what I've gotten here. And so you might say, what on earth are you doing, Professor? Well, a lot of calculations, but see what I've gotten. 2 is equal to 8 times 414 minus 5 times 662. You might say, what is that for? What does that mean? Well, it means that I can write my GCD, this is the GCD of these two numbers, as a linear combination of these two numbers. And that is always true. So this is called bizus theorem. Well, here they call it bizus theorem. I actually normally don't call it that, but okay, I just stick with the book says. Or they call bizus identity. Bizus identity, that's how they call it. Bizus is also again a mathematician, but from much more recent mathematician from the 19th century. Well, I don't know whether that's recent, but I mean compared to Euclid and Eratosthenes that we were talking about. So Bizus identity says this, that the GCD of A and B is a linear combination of A and B. What does that mean? That means you can write this as K times A plus L times B, where K and L are natural numbers? No, they can be negative, so integers. So there are coefficients K and L, and by the way, they're not unique. So some KL not unique, but you can find KL so that you can write the GCD as sometimes a number of times A plus another times B. Now, of course, the GCD is normally very small, so it is clear that one of these numbers is going to be positive and one of these numbers is negative. So what is this here? Well, here we see if you take 8 times this number and you subtract 5 times the other guy, then you get exactly 2. So in other words, in this scenario, if A represents 414, then this is the K in my formula. Okay, and then the L in my formula would be the -5 here. So, Bizus identity says you can always do this, and I showed you how you do this. Now, it is a little bit of work, yeah? So let me do it one more time, and then we'll stop, and then let you try it yourself. Now, the coloring it drives one mad, right, if I do this. So instead of just taking different colors, I'm just going to circle my numbers. Okay, so again, we always start from the equation. So we're going to go up now, and we start from this equation, not the one where we have 0. That's already is the end of the story, right? So it's the one where we have the remainder 1, which is the GCD, right? So I remind you, this is the GCD, okay? And this was the number 2 that I used, and this was the number 3. Okay, well, perhaps I should, let me do this a little bit. So, okay, let me rewrite it because I made a little bit of squiggling thing here. I don't know what I did this. 2, and that was... I'm not going to use the colors anymore, but I want to... I don't want to circle this. Okay, sorry about that. So, okay, so I start from 1, and I use this equation that the last one, to rewrite 1 as 3, but a circle. See, 3 is a colored number, so the colored numbers I'm now going, instead of coloring, I'm just going to circle them. -1 times 2. One of these numbers has to be circled. It's this number. And you might say, why? Okay. Yeah, but these numbers, you get confused by these numbers, because what you're going to do now, you take the smallest of the circled numbers, and that's the one that you can, the equation just above that is going to tell you what it is, right? This smallest one is this guy, and I can write it as in this combination, right? So this means that, so this is equal to the 3, I'm not changing that, minus 1 times, and now I replace 2 by the combination I get there, 8, but it's a colored number, so I circled it, minus 2 times 3. Which of the, is the 2 circled or the 3 circled? It's the 3 that is circled here, right? See, that's what I'm saying, because there are 2's and 3's and numbers all over the place, but you have to keep track of what are the circled numbers and what not. Before I go to using the next equation, I have to first simplify this expression because it has 2 circled trees in there. So you think of these circled numbers as like terms. Okay, so you treat a circled number differently than a non-circled number. So circled numbers are considered like terms of just you circle the same number. So we have, if I would rewrite this, I have a, how many times do I have this circled tree? I have it once here, and how many times do I have it here? Minus 2. Minus 1 times minus 2 plus 2. So 1 times here, 2 times there, so 3 times there. So notice there's another tree here, but that's not a circle tree. Okay? And then what about the other number? But it's 1 times circle 8. Now I'm done, and I can go to this guy, which tells me, okay, the smallest of your circled numbers, which in this case is 3, can be rewritten. Okay, let's do that. So it's going to go a little bit higher up here, so this is where I do this. It's 3 times. I'm going to replace 3, and I'm going to keep the second term. The first term is then becomes 19 circled, because it was a colored number there, minus 2 times 8, and 8 is a circled number here. Okay? Before I go on, I need to simplify, because you see there are now 2 circled 8s. They have to be combined. So we have 3 times 19. Oops, circle 19. And how many combinations of 8 do I have? Be very careful always, because there's always these coefficients in front of here. So 3 times minus 2 is minus 6. We have a minus 1 here, so altogether minus 7. Okay, I'm done with this guy. So now I move to this one, which should give me how to write the smallest of my circled numbers. Exactly that. That's my 8. So I can use this to write this as 3 times 19, that's not a small, I'm replacing this one, 8, and I'm replacing 8 by 65, which is a circled number, minus 3 times 19, and it's the 19 that is circled here, not the 3, the 3 was nothing to, that was just a coefficient. Okay, I get a little bit, I should have given myself a little bit more, I could have, no, that doesn't help. Before I use the first one that I started with, the last equation, if I go back upwards, I need to simplify again, because as always we will have the smallest number will occur in 2 different spots, so we have to combine it. So that will be 3, how much is that? Let's figure it out. It's a 3 there, and a minus 7 times minus 3, that's 21, plus 3, so 24. You see, these numbers here in the front can also be big numbers, right? In the previous case were small numbers, but they can get big too. And that's why we have to keep a track of what's the circled number and what are these coefficients, okay? So that's that, minus 765, because I'm not changing that. I now use, finally, my last equation, that will be the end of the calculations. I'm using this to replace the circled 19, the smallest of the 2 circled numbers, okay? That is 24, and that is 84 circled, because it's colored, minus 1 times 65. It's the 65 that is colored. And then the second term, of course, I don't replace. And finally, last step, okay, let me get even more space here. I have to combine these 2 circles 65, and I'm done. I get 20, what is that? I get 24 times 84, right? That's nothing combined, but now combining the 65, so what's the coefficient there? We have a 24 times minus 1, that's minus 24, and a minus 7, that's minus 31. And these are now the original two numbers that I worked with, right? Because there's no equation anymore, so I'm done. And what it says is that, it says that 24, so remember this is all equal, right? These are all equal and start from here. So 1 is equal to 24 times 84 minus 31 times 65. And let me circle them again. These were the two original numbers, and this was the GCD of these two numbers, and this tells me how I can write it. And you see, this is not easy at all, right? This is not something you can guess. If you would have to try this, so if you know the bizus identity, we know you can do this, but if you have to try this, how many combinations do you have to try before you hit 24 minus 31, right? And by just the size of this thing, 24 times 84, that is 2016, so this is this number is just, if you don't trust me, this is 2016, and the other number, 31 times 65, is 2015. So this number is 2015. So indeed, the difference is 1. Okay? So that's the technique of the bizus identity. To find, using the Euclidean algorithm to find bizus identity. And that's an important technique, and I will quiz you on that. So it does two things. It calculates the GCD of the number. It also allows you, by the way, remind you, to calculate the LCM of these numbers by using this trick. And it also provides you, if you unravel it, if you work upwards and do it the right way, and I really strongly suggest you do the circling that I do. And so in same thing here, right? Instead of colors, you can keep circling things all the time. You see, there's always the same numbers that get circled, and then you don't get confused, because there's a 7 here and 8 there. Okay, which one is what, right? So you need to keep track of what it is you're trying to do. You're trying to get to these two numbers, and you're writing them as a linear combination of 1. If you're gonna replace this, I'm just saying here, for instance, here, there's a 3 here. If you use this 3 to replace it by this combination, you're completely off track. You won't get what you want. Okay, you have to do this very systematically. Okay, I'll do a review also for this in another problem like that, so I'll do one more calculation like that so you can practice, but please practice this until you get the hang of it.